Okay, everybody, today we're going to learn about machine forgetting. So, why study machine forgetting? Because it can actually teach us a lot about machine learning. And if we're also interested in things like security problems, privacy problems, this becomes pretty essential. So, machine learning forgetting and the study of it is not new at all. It's actually been around since we were starting to build machine learning systems. So, I have this example from the 60s where they're talking about memory access of the models that they were using at that time and how if they didn't have memory access, the machine learning model would fail by forgetting, right? So obviously we have much different models now. So what's our motivation to study forgetting? Sometimes we can study forgetting so that we know what's essential to learn. And if we know what's essential to learn, we can also decide, you know what, all of this extra data that we have is actually non-essential to learning the tasks that we have, which is really great because we store less data, we, learn more efficiently, we waste less time, we spend less carbon, all of those things happen, right? So we can just efficiently and effectively learn what we want to learn if we know exactly what we need to learn to get the task done, which also goes to the minimum required data. What's the most representative data for the task and maybe the populations that we're trying to learn? So can we effectively go about data collection in a way where we're very intentional of what we need in order to make our machine learning work and to avoid data quality mistakes or things like this? Data poisoning is a big topic right now, but basically, if we have learned something that we want to forget because it's a poisoning attack or something like this, then we can do that. And we can also do that for privacy. So obviously, maybe you found my work by my work in machine learning memorization. If we have memorized somebody's personal details, and then maybe we can target them and forget them. So more on this topic coming soon. So what is forgetting? We're going to pick just one definition. There's many. This is one definition from one of the earlier papers on kind of today's deep learning models and how do we forget in them. We're going to pick an example subset. We want it to be representative of the data that we have in the entire training pipeline. We're going to track the classification and prediction result of these data points as we go through the training process. So as we're doing each epoch, we're going to take a look at this subset and see, has the performance increased or potentially decreased? If there's a decrease in whatever we're using as a measurement, true positive or false positive, or some ratio of the two, of what's happening with these particular example subsets, we're going to store that moment, that epoch, that timestamp as a forgetting moment, and we're going to measure exactly how much forgetting happened. So how wrong the answer was in comparison to what it was before. And then at the end of training, we're going to try to analyze these events. Now, this is just during normal machine learning, we can do this because it can teach us things about the data that is actually representative for the task and the population that we're trying to learn. So when these authors did this, and you can check out all of the links to the research in the description, and I have a blog post too walking through all of this for you, we can see that the unforgettable, so the things that did not ever decrease in accuracy once they were learned, that unforgettable is, to human eyes, quite typical examples of what we would expect to see when we think of these different categories that we see here. And the forgettable images, in contrast or in comparison, we can see are atypical, are kind of interesting, maybe strange viewpoints, maybe different directions, maybe only partial of whatever the object is in the photo, right? This is a really simple machine learning data set, but this is something that we know even for larger models and larger training sets. This is from related research on forgetting, and it basically proved out what makes a lot of sense if you think about it. The bigger the model size, the less likely the model's gonna forget, and the less information the model's gonna forget. So they studied forgetting over many, many epochs, and they studied it over many, many network sizes. So how many weights and biases, parameters do we have in the model? And obviously, the higher the parameters, the higher what they call the forgetting baseline, which means you're never going to forget anything that is above that baseline, right? So that basically means that more parameters, less forgetting, which we also know relates to less or more memorization. And this is again studied on a meta level in this paper, where they tried to find subdivisions within the examples and classify them based on forgetting time and learning time. So we can see here that what exactly what's been found time and time again, typical examples are easy to learn and hard to forget. That's just the way it is, right? That's the basics of machine learning pattern recognition. Then we see here mislabeled examples. This is data errors. This is oddballs that don't really fit into the learning task. This is, I would argue, a lot of poisoning examples fall here too. They're harder to learn, but they're easy to forget as long as you have representative data. Then we have outliers, just outliers on their own, rare ones. They're harder to learn. They are medium, easy to forget. You can forget them, but it kind of depends on the task and the data, right? And that's when we get to, there's a link between rare examples and what are called in the paper complex examples. And these complex examples are exactly where I think, my personal opinion, the most problematic memorization occurs. These are extremely hard to forget, and they're also hard to learn, and that's because they contain useful information. What do I mean by that? Well, either they represent a class or a class in combination with a task that is high complexity. That means that there needs to be a lot of information learned about this one class in order to guess it correctly. The second type of complexity is when an example itself is complex compared to its peers, compared to the other examples in its class or in its population. And this complexity is certainly related to information theory. And I have a video on information theory, so check it out if you're new to information and learning theory, because this is exactly what we should be thinking about, what we need to be thinking about in order to design these systems and decide what complexity are we going to memorize and what do we want to actually not learn because it might be dangerous to humans, right? To their privacy, right? So this is a cool way of starting to think and reason about it. It also shows us if we have a bunch of typical examples or mislabeled examples, we can kind of avoid these by studying forgetting, right? Or we can collect less typical examples and still learn the task. And we can avoid mislabeled examples by actually studying how they get forgotten easily. And these are all qualities of machine learning. The data set population that we have is a non-trivial part of how we learn when we're doing machine learning. And the representation of that data set for what we're actually trying to learn, the task at hand or the population at hand, is essential for us to understand if we're going to understand what we need to forget, what we need to learn, and how these are going to interplay during our training and our model development. The model size and architecture is absolutely related to forgetting. The bigger the model, the less that is likely to forget. That's just the way it is. Inlier and outlier examples. So outliers are going to be harder to learn, but they may be complex. They may contain a lot of information. And then they're going to be memorized because that's exactly what we're asking the model to do. We're saying, please learn this really hard example. Guess what's the easiest thing to do, especially if you have a bunch of parameter space? You're going to store a lot of information about that example, okay? And the inliers, we don't even need all of them in the training data set. Let's be real with ourselves. We don't need as big of a training data set if all of the dogs are perfectly pictured in the center of the image with lighting, right? That's just not what we need, okay? So maybe we should start thinking about that too. And complex versus easy. And this means we need to actually start wrapping our heads around information theory and learning theory and how it relates to how we build today's machine learning systems. Now, I'm going to have a hot take right here, and that's basically that there's been a lot of cloud providers that are just very, very happy to sell us as many GPUs as we want to use and as much database space, S3 space, whatever that we want to use. Learning how to do this stuff efficiently is going to save you time. It's going to save you money. It's going to make you a smarter machine learning engineer. And it's certainly going to save you cloud costs. So just a thought that it might be useful to know. And all of these qualities, surprise, are also related to memorization. If you're just catching up, take a look at the other videos in this memorization series, and I'll see you next time.